All right, section 12.2, we're taking a look at differentiation and integration in these vector forms that we've been working with thus far in chapters 11 and the first part of chapter 12. So first, the derivative definition is going to look much like you saw in Calc 1 about a year ago, many of you. We're not doing the limits part of it, but this is the definition. Everybody just breathe. All right. But the definition is the same, okay? It's the same definition that you have seen before. The derivative of a vector valued function r of t is r prime of t is the limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t. When we do it in calculus, I usually put h's in there for all those delta t's. This is true for all t for which the limit exists. Have you seen this notation before? This one right here? No, that's a no. Okay. This notation, jot it down. What is in linear algebra? Yes, Dylan. What does it mean?
For all.
It means for all. So that's a notation. Well, there will be pieces that come about every now and then. And so for all t for which the limit exists, if r prime of t exists, then r is differentiable at t. If r prime of t exists for all t in some interval, then r prime of t is differentiable on the interval. Okay, this is a combination of the vector things we've been doing, derivative definitions we've seen before, and there was two definitions of derivatives that had this variation, or had this form, I should say, when we did them in Calc 1. And when you saw them there, it talked about finding a derivative at a point, and then it talked about finding a derivative on an interval, and there wasn't any difference. It's just whether or not it's actually able to be done at a particular point as opposed to on an entire interval or maybe on the whole domain, like negative infinity to infinity. So these details at the end are just saying that your derivative could exist in some small place, it could exist at one single point, or it could exist sort of everywhere, okay? And all of those definitions would be similar and so structured similarly. Okay, so in particular, if we have r of t, and it's equal to f of t times I, or f of t I plus g of t j plus h of t k, where f, g, and h are differentiable functions of t, then the derivative vector, right, r prime, is going to be the derivative of each of the functions at those I, j, k components. Okay? Which I think is what Adrian was saying when he looked at it before, right? Yep. It's just like you would expect it to be. Okay? It's very intuitive. And we're going to do it just like you would have expected to do it for those each individual functions if you were doing a derivative or like a derivative gateway or otherwise. And so we're going to be given these three functions. So in one particular problem now, instead of just finding one derivative of one thing, you're potentially going to find three different derivatives of three different functions, right, if it's a three-dimensional one. So when we have this equation right here, vector equation, r of t, it's going to have the components, and this is in component form without the ijk's, right, but with those brackets, those triangle kind of brackets, e to the t squared e to the 2t, and secant 2t, those three pieces. So we're going to find three derivatives, right? So we're doing r prime of t. You can write it in IJK format. I'm going to stick with the format I'm given, which is this component form format. E to the t squared. What property am I using? What property is this?
Chain rule.
Chain rule. Thank you. It's chain rule. So tell me what it was, Adrian.
2e squared, t squared.
2t e to the t squared, right? Okay. So the derivative of e to a power is e to a power. The derivative of that power, the chain rule, is t squared becoming 2t. All good?
Yep. Excellent.
Okay. The next one was t squared e to the 2t. What property am I going to be using here? Product rule. You're right, Dylan. It's product rule. So we have to do them independently of one another and multiply by the original. I always do my first one as writing it down. Some of you do it the other way around. That's fine. It's t squared. And then what's the derivative of e to the 2t? Yeah, I'll write it the way you just said it. 2e to the 2t. And then product rule has addition next. And now we're going to do the derivative in the other order. So the derivative of t squared is 2t. And then I have the second part rewritten e to the t squared. Or e to the 2t, excuse me. And then the last component is secant of 2t. So what is the derivative of secant? Secant tangent. And it's secant tangent of whatever the angle is already, right? So it's secant 2t tangent 2t. And then what do we need to do? times 2. I'm going to move it in the front. So we're going to multiply that by 2 for the derivative of the inside. The only thing that there is to clean up, perhaps, is the fact that there's a dot right there in the second one. And so we could rewrite that a little bit more clean by moving the 2 in front and writing it as 2t squared e to the 2t. And then everything else would remain the same. As such. Sorry, I'm off screen, so you can't see my... There we go. Okay, all good? Yeah, okay. So then we're going to find some derivatives and some dot products of some derivatives and some cross products of some derivatives, right? There's a lot of details going on this particular direction set. We're going to do them one at a time. So the first one says we're going to find r prime of t. So that's fine. It's in IJK format, so I'll use the IJK format that it's in. So what's the derivative of 1/2 t squared? It's t. So this is ti. What's the derivative of tj? Just the j, or 1j if you prefer, right? Negative as well. How about the derivative of 1/6 t cubed? 1/2 t squared, right? The 3 comes down, simplifies, and so forth. And then we have k. So that's the first part. That's part A. So we've done part A. Part B says that we're going to do our double prime, second derivative. So derivative of derivative. I don't know why I have that put on the end. I don't need that here. I was using IJKs. All right, so what's the derivative of ti? It's just I, or 1i if you want. How about the derivative of negative j? That'd be 0. If you want to write 0, you can, or you can just leave it off. I'm going to leave it off. And then what's the derivative of the 1/2 t squared k? T, k. Okay? Well, that was B. I don't know why I wrote A. All right, C. So on C, it wants us to take the dot product of the last two things that we found. Dot product. So we have r prime of t dot r double prime of t. And so we're going to multiply component-wise what's in front of the i's, the j's, the k's. So on the first one, I have t times the second one's I component, which is 1, plus the first one's component in front of j, which is a negative 1, times the second's component from a j, which is a 0, the one I didn't write down. And then on the third one, I have the 1/2 t squared that will be multiplied by t. Is that all good? Okay. So if t were a number, this would be giving us a scalar. It's not a number, right? Because that's what we saw happening back in chapter 11. We actually have function components. But we can consolidate what's here. We have t, the middle part's 0, and then I have plus 1/2 t cubed.
Do we stop there or do we go further?
There's nothing else to do further.
Okay.
Yeah, so that is the end of that particular part, part C. What does part D say we're going to do? So that's C. It's kind of long written there. D's the last one.
Cross product.
The cross product. So we're going to do r prime of t cross r double prime of t. So setting up the cross product, I'm going to set up the matrix for it. If you want to jump to just doing the individual determinants, you certainly can. It helps me to see the matrix, so that's what I'm going to do. So I'm going to do the I, the j, and the k. So on the first one, I have t, negative 1, and 1/2 t squared. On the second one, I have 1 and 0 and t. Did I get them all in there right? Okay, I think so. You can expand along those if you would like. I'm going to actually just jump the expansion, and since I wrote down the matrix like this, okay? So I'm going to have the I multiplied by negative 1 times t, and then this piece is going to be 0. So this would be negative ti. And then we're going to have j. So the j component is going to be subtraction, actually. But I have, this is t times t is t squared. And then on this diagonal, I have minus 1/2 t squared. So if I have t squared from one diagonal and minus 1/2, 1/2 t squared, I'm going to get what? I'm going to get a half of a t squared. But there's a negative that's coming from the formula itself already, so I'm still going to end up getting a negative 1/2 t squared times my j. I think it's 1, 2. And then we're going to do k. So k over here, this t times 0 is 0. 1 times negative 1 would be negative 1, but it's subtraction. So we have subtraction of negative 1, which would be addition. So this would then be plus k. Let's check and see if that's what I have in my notes. Yeah, I think so. Looks good. Okay, any questions on that?
Wait, why is it subtraction?
Should it be J?
Yeah.
So when I am expanding along these two multiply. These two multiply gives me 0. When I multiply these, I get a negative 1. But when I multiply going up that diagonal, I always subtract the value. So it's minus the negative 1, which should be positive k.
Cross product.
But for the J.
For j, what is your question on j, Sophia?
Why is it minus 1/2 t squared?
So let's see. Let's undo those pieces. So with j, we were looking at this piece. That's t squared. And then you subtract these pieces, so we get this. And then the middle component with j is always a subtraction. It's always. It's addition, subtraction, addition for the i's, j's, k's when we do cross products.
Isn't it negative 1/2 t squared?
So this piece right here, if I had t squared minus 1/2, would be 1/2 t squared.
Oh, yes. I see.
You got it now? Okay.
I wonder how they just figured that kind of stuff out. Just stumble
I don't know.
upon it.
People that have a lot more intuition is the word I want than I do for sure on how to play with things.
I don't know.
Okay, you ready for another definition?
Yep.
Yeah. Okay, we're going to have the definition of smooth. So we say that a curve traced out by a vector valued function, r of t is f of t I plus g of t j plus h of t k, is smooth on an interval I if r prime is continuous on I and r prime is not equal to 0 except possibly at the endpoints of I. So we don't care so much about the endpoints, we just care that all of the interior points, we do not have a derivative that's 0. And we have a smooth function.
I'm just a little tired, just want to make sure the R with the little hat on it, that's just a vector, right?
Yeah, it's a vector valued function.
Just wanted to make
We're
sure.
working with vector valued functions here. Yes. Okay, so we're going to be checking to see if something is smooth, and this is the definition we're using. We're wanting to make sure that the derivative is continuous and not 0. It could be 0 on the endpoints, that usually doesn't even matter, but basically continuous and not 0. That's our goal. So in particular, we start with, in this case, a vector valued function. We have given here, it's actually only got 2 dimensions, right? An x and a y, or an I and a j. And we're going to find its derivative first. So the first thing we need to do is the derivative. So what is the derivative of t to the 4th minus 2t squared? 4t cubed, and then minus 4t. And the second one? 2t minus 2. Okay. So the things that we do when we're looking at this to decide if it's smooth are continuous first. And we need to make sure that each component is continuous. The first component is a polynomial, and so is the second one. And what do we know about polynomial functions? This is chapter 1 of our book. It's a long time ago, I know. Well, we know that polynomials are continuous. There's actually theorems that talk about them. But if you think about what it means to be not continuous, it does make sense. So not continuous would mean that you've got jumps. Do polynomials have jumps in the graph? No. Not continuous would mean there's holes in the graph. Do polynomials have holes in the graph? No. We don't have any of those kinds of features. And the last one would be asymptotes. Do polynomials have asymptotes? No. So it check marks off all the things that you can't have as not having them, right? It doesn't have those features. So kind of by default or process of elimination, it's going to be continuous. So these two functions are continuous. That's not a problem. So the second thing that we're supposed to check is that the derivative does not equal 0. Now, these things do have the possibility of equaling 0, right? So we need to figure out if they do, what does that look like? In particular, we're checking to see if 4t cubed minus 4t, not if, but where this is equal to 0, and where 2t minus 2 is equal to 0. That's what we're looking for. We need both of these to be the possibility of equaling 0 and to see where that might happen. Okay, so the first one, how do we solve 4t cubed minus 4t equals 0? Factor out of 4t. What will that leave us with? T squared minus 1. Okay, what's next? We'll factor this one. So what's the factoring of t squared minus 1? T minus 1, t plus 1. And where will these t values actually equal 0 then? 1 and 0 and negative 1, right? Okay, then. What about over here for the second part, for the j component, 2t minus 2? This is t equal to 1. Okay? Now, take a look what this says. We want to make sure that r prime does not equal 0. R prime is a vector. What does it mean for a vector to equal 0? Right? If I have a vector, even a three-dimensional if you will, what does a 0 vector look like? Yeah, it's going to have zeros at the same time in all three of those locations, correct? So while we found locations where the first component is equal to 0, at all three of these locations, it is not true that the second component is equal to 0. Do you see that? There's only one that they match on. There's only one location where they both are 0 at the same time. And both of them being 0 at the same time is what's going to create the vector itself to be the 0 vector. So this location right here where t is equal to 1, and this one where t is equal to 1, does create something that's not smooth. It's not smooth at that point. But at the t equals 0 and the t equals negative 1 values, we're fine. Right? One component's 0, the other one's not. So we don't have the 0 vector there. So what can we say? Well, the directions say to determine if it's smooth. Well, we found out that it is smooth most of the time, right? R of t is smooth. Except where? Yeah, it's except at t equal to 1. Right? It's smooth everywhere else. It's as good as anything, I think. I've got it written a slightly different way in my notes, but this works just too. Okay, it is smooth, except at this one location. Does that make sense? Now, play with the idea just a moment and say, let's say that the first one ended up giving you 0, negative 1, or 0, 1, 0, negative 1, just like it did. It looks just like this. But the second component said t equal to 2. What would we say then? It's smooth everywhere, right? There is no location where both the components were 0 at the same time. Is that a possibility? Well, of course that's a possibility to have happen, right? So don't be surprised if you see that happen as well. You don't have to have a 0 that's going to happen in all the locations at the same time. And the more locations, the more specific, right? You'd need a 0 if you had a three-dimensional and three vector spaces. That's not what I meant to say. And 3 components of the vector, okay? All right, let's do integration. So if we have the vector valued function f of t, g of t, h of t, we can define the integral as the integral of each of the individual components.
So just like the derivative one.
Just like the derivative one. So, and the notation, that's very intuitive, yes. And just like the notation before, if you take the antiderivative of f of t, you get capital F, right? And the small g of t, you get capital G, and so on.
You know, I'm not gonna lie, I really thought there was gonna be some weird curveball to these. I was waiting for it.
There's not a weird curveball. There is an interesting thing that shows up on the notation for this that we'll be mentioning when we get there, but there's no major inconsistencies with what you should expect. Okay? Okay, you ready for one? we're going to take the antiderivative of the vector valued function 2t minus 1i, 4t cubed j, and 3 square root of tk. So we're going to do it component-wise, of course. And so this is going to give us ijk's. It's already an ijk, so we'll leave it that way. All right, so what is the antiderivative of 2t minus 1? T squared minus t.
Plus C?
Thank you. Plus c. We're going to call it plus c1 because we're about to have a c in each of the locations. Okay? And they aren't going to be the same, or at least there's no reason they have to be. So I'm going to call it c1. I'm going to show you a variation of this as well, but this is one option. The next one, let's see. We have 4t cubed j. What is that? T to the fourth plus c2 j. C2, it's different than the C1, or at least potentially so, right? And then how about the 3 square root of t? That's the messiest one. Okay, so what do you want to say, Adam?
T to the 1.5.
2t to the 1.5. Wow, I'm not sure if I can do that. So you did 3t to the 3 halves, and then you divided it by your 3 halves. So we should have gotten a 2. And then I will write it as t to the 3 halves, or even better, actually, let's do this. Square root of t cubed. Is that okay? Works great. It looks like the one we started with. So, and then I need plus C3, right? Okay. Is that all right with everyone? Okay, there's one other way you could write this. So this is sort of the I don't know, more unique thing that we have done. So we could do t squared minus t I plus t to the fourth. I don't really need parentheses at that point. T to the fourth j plus 2 square root of t cubed k. And then we could actually put plus c at the end like this.
Oh.
It's a vector, right? This ci, or c1, c2, c3 is another vector, and it's a constant vector. So if you don't want to write it in each component and you just want to put it as a plus the vector c at the end, you can do that.
That'd probably be a little simpler.
It is a little simpler.
Be on the edge of everything, way out to the side. Make sure you check if you got this.
For those of you who don't know, what Connor likes to do is he likes to put plus c down the side of all the things that are antiderivatives so that he doesn't forget them at the end, but they're very far away from the problem. They're nowhere near
It's
them.
on the edge of the paper.
It's edge of the paper.
Right on the edge.
Yeah.
I took
Yeah.
the gateway the first semester, and I wrote.
Let's take a look at number 5. So number 5, same directions essentially, except that it's a definite integral, right? We've got limits of integration. So we don't need c's at all when we do definite integrals, right? Yeah. Okay, so let's find the antiderivative for each of the pieces first. So what is the antiderivative of a cosine t? It is a sine t. I. What is the antiderivative of a sine t? Negative a cosine t, and this one's j. And then the derivative of k? T, k. And we're evaluating this from pi halves down to 0. So we're going to do a sine of pi halves I plus minus a cosine of pi halves j plus pi halves k. And then we're going to evaluate all of them at 0. I'm going to put the 0 one underneath. It's a sine of 0 I minus a cosine of 0 j plus 0 k. All of that is subtracted from the original. Some of these things zero out. So let's just go through them one at a time. Sine of pi halves. What's that number? It is 1. Okay, so I'm going to write it in a different color just nearby so that we can adjust these in a moment. This piece is 1. What is cosine of pi halves? That one's 0, so this whole thing's going to be 0 now. And of course, pi halves is just pi halves. Okay, what is sine of 0? That one's 0, so this whole thing is 0. And what is cosine of 0? That one's 1. Okay, and then of course the 0 at the end zeroes itself out too. So on the I components, this is the only piece that remains, AI, right? And this one subtracts off, but it's 0 anyway, so I have AI. On the J component, this first one is 0, and then I've got minus the negative 1. So I'm going to end up with plus, and I've got the A with it, so plus AJ. And then on my K component, I have pi halves here, but I have 0 here, so I just have plus pi halves K. Okay? Might not like the fact that there's A's in it, but they don't really cause any problems. They're just standing in place for a number. All right. Ready for the last one? All right, number 6. Find, I don't know why that's listed there twice. I should probably edit that slide. Find R of t that satisfies the initial conditions. So again, this goes back to things we've done in Calc 1 and Calc 2. We have the C, right, the vector C or the C1, C2, C3, whatever. We have them showing up. But when you have an initial condition given, it means you can figure out what the C's are supposed to be, right? So if you remember, the reason that we put plus C on the end of things when we do antiderivatives is because when we take derivatives, what we are worried about is shape. We figure out what the shape is, but we lose the location. So the additional, the shape, so imagine something that's a specific shape. Let's imagine the shape of x squared, because everybody has that picture in their mind immediately when I said it, right? Simple curve, we know what it looks like. If I took x squared and I shifted it up or down, no matter where I shifted it to, its derivative is going to be 2x, correct? Because its shape didn't change. So the reason we put the plus C on the end of that is to signify the fact that it could be shifted up and down from where we are, and the shape would have retained, we would have retained the shape. Okay? So this allows us then to find the shape's actual location, the C1, C2, C3, or in this case, we just have 2 components, so C1 and C2. All right, so we have to find the antiderivative first. So the first thing we're going to do is to take an antiderivative. So what is the antiderivative of 4e to the 2t? Four e to the 2t. Yeah, it's 2e to the 2t. Right? It's 4e to the 2t divided by 2. Okay? That 2 is catching several people on a gateway, I think. Everybody kept saying, where'd that 1/2 come from? I said, well, it's a U substitution, just not a very exciting one. My Calc 2 class was having the same problems where there was a 2 that kept showing up as a fraction denominator. All right, so this one is the I. Oops. Let's go ahead and put the C1 in here right now. If you want to put it at the end, you can do that. I'll do it this way. And then what is the antiderivative of 3e to the t? It's the same, actually. 3e to the t, j, well, for consistency, plus c2, j. All right, and this is supposed to equal the vector 2i, because that's what it says it's supposed to equal when I'm done, yeah? I shouldn't actually write it that way. It's going to equal 2i, what is r is 0. That's what I missed out on. I was like, where did that go? So when we have r evaluated at the vector, at the t value of 0, so 2e to the 0 plus c1 I plus 3e to the 0 plus c2 j. This is going to equal the vector 2i. And for the sake of what I'm comparing, I'm going to go ahead and write in plus 0j. Okay? So we're trying to figure out what c1 and c2 have to be to make that happen. Well, what this is saying is that the 2e to the 0 plus c1 has to equal 2. And the 3e to the 0 plus c2 has to equal 0. Okay, so we've got e to the 0 in here twice. What's e to the 0? It's 1. So we really just have here 2 plus c1 is equal to 2. What's c1? It's 0. And we have 3 plus c2 is equal to 0. What's c2? negative 3. So our vector that we were looking for, we'll come back down here, r of t with its initial condition utilized is actually 2e to the 2t I, right, because it's plus 0, and then 3e to the t minus 3j. What do you think? This should feel just like what we've done before, just 2 or 3 at a time, right? Yeah, just 2 or 3 at a time.